Okay, we're on section 1.3. We're going to start right here where it says vapor pressure. Okay, so we're going to continue our talk about gases. And you know that if there was a puddle of water outside, eventually that puddle would evaporate. And the reason is because in a sample of water, the different particles have got different kinetic energies. So there is a distribution of kinetic energy that looks like a bell curve. It looks similar to this. And when you're at a lower temperature, obviously there would be lower kinetic energy. So that's why this curve is shifted to the left. At higher temperatures, you would see more particles with higher kinetic energies. That's why it's shifted to the right. Now, the amount of kinetic energy that water particles would need to escape the liquid phase and enter the gas phase is shown by this little shaded region that's underneath here. So at a lower temperature, this is showing you the number of water molecules in the puddle that would have enough kinetic energy to escape. It's not much, right? But as you move to the higher temperature, obviously, you're going to have more particles with enough kinetic energy to escape and go into the gas phase, okay? John Dalton put water in a sealed container and he inverted it over itself and noticed that initially when it was filled with water, there wasn't any pressure above that water that was coming from water molecules that had evaporated. But over time, what happened was the water vapor accumulated above the liquid. So anytime we collect a gas over water, since we actually know the amount of water vapor or the vapor pressure that would accumulate above liquid water if you had it under these conditions at various temperatures, we can use that as a reference value, and then we can collect a gas over water. If I decided to collect like hydrogen gas over water, then I would have a tube where it bubbles through and then it bubbles above the water. And then as it gets collected above here, I can figure out what the pressure is of it because I know what the vapor pressure of water is above its own liquid at various temperatures, okay? And I'm going to talk about more about that in a second. For now, I'm just introducing the concept of vapor pressure. So vapor pressure, which is often abbreviated as VP, is the pressure caused by the vapor of a substance. And it explains why we can smell some liquids like right away, like nail polish remover, which would be acetone. Also explains why you can smell things like gasoline or rubbing alcohol right away, because those substances go into the gas phase immediately. And then it also explains why you can smell things like black licorice right away, okay? Let's go to the next page. So here you can see they've given you a table of the vapor pressure for water at various temperatures. So if we're at a temperature of 0 degrees Celsius versus 100 degrees Celsius, obviously the vapor pressure of water is going to be dramatically different. So at your higher temperature, you've got a much higher vapor pressure. So what this says is as temperature for water increases, so does the vapor pressure, okay? And from this concept, they come up with the definition for the boiling point of a liquid as well. So the definition for the boiling point of a liquid, which we've mentioned in chapter 2, is the temperature at which the vapor pressure equals the atmospheric pressure. So this is why water boils at a lower temperature in the mountains, because the atmospheric pressure drops in the mountains because there's less air particles above you. And that means the vapor pressure of water doesn't have to be as high to equal the atmospheric pressure, and then water boils, okay? Now, up at the top of this page, there are a couple of things that pertain to vapor pressure that I'm going to mention. vapor pressure depends on the chemical structure of something. So that means if it's polar or if it's nonpolar. And the second thing it depends on is temperature. Obviously, at higher temperatures, you would have a higher vapor pressure. Okay? All right, now let's take a look at the graph. I will give you this table, by the way, if it's ever needed. And you may want to earmark this page because when you're doing a problem that mentions you're collecting a gas over water, you're going to want to use this table as a reference. Okay, so what they'll do is in the problem, they'll mention what temperature you're at. They won't necessarily give you the vapor pressure of water at that temperature. They'll assume that you know that you need to look here in this table to get that value. The only thing you need to watch out for is make sure you look at the unit here, make sure that that unit matches the unit in the problem. Otherwise, you'll have to convert it, okay? Okay, now, the graph that is on this page shows you the different boiling points for liquids depending upon the pressure that we're at. So the reason why they give you this table is because this is how you would determine the normal boiling point of a substance. So here we've got diethyl ether, that's the green curve, ethanol is the red curve, and water is the blue curve. Here they have pointed out 760 torr. And the reason why they've done that is because this would be the pressure, the atmospheric pressure, I should say, at sea level. So anytime you're at sea level, this is where you would obtain the normal boiling point of a liquid. So you would follow this dashed line across and you would see wherever it intersects with these different curves. Okay, so here we've got 34.5 degrees C, 78.5 degrees C, and 100 degrees C. So those are all the normal boiling points of those liquids. Okay. When you're ready, go to the next page. On the next page, they've given you a figure that shows you the different altitudes and how the atmospheric pressure and the boiling point changes. So here we've got sea level, which would be 0 feet. And up here we've got 29,000 feet, which is going to be where Mount Everest is. So we've got Mount Everest at the top, Mount Rainier in Washington, and then Clingman's Dove at Smoky Mountain National Park. On the right-hand side, we've got the atmospheric pressures, and then we have the boiling point of water. You can see that the atmospheric pressure is going to be the highest at low altitude. And think of it as you have more air particles above you, therefore you would have a higher atmospheric pressure. There's more pressing down above you, okay? And then up here at Mount Everest at the top, this is where you would have the lowest atmospheric pressure because you would have much fewer particles above you pressing down, okay? Now, in terms of the boiling point, you'll notice that the boiling point is the highest near sea level. And that's because you have to get the vapor pressure of that liquid, in this case water, to meet the atmospheric pressure above it so that it boils. And the atmospheric pressure is going to be the highest at sea level. And then your boiling point would be the lowest at high altitude, due to the fact that your atmospheric pressure dropped when you went up to that higher altitude, okay? All right, let's take a look at intermolecular forces and boiling point. So intermolecular forces is going to greatly affect the boiling point of substances. Let's take a look at a few here. Here we've got diethyl ether, ethanol, and water. I'm not going to focus so much on mercury. Mercury is going to have metallic bonds. We don't really talk that much about things like that. Diethyl ether is slightly polar. So that means it's going to have London dispersion forces and dipole-dipole forces. Ethanol has got a hydroxyl group on the end of it because it's an alcohol. So that means it has the ability to hydrogen bond. So it's going to have London dispersion forces, dipole-dipole forces, and it has one location where it could hydrogen bond. Water technically has got two locations where it could hydrogen bond. Okay, so it could hydrogen bond here or here, right? So we've got two hydrogen bonds. These things will influence their vapor pressures and their boiling points. So here you can see that the vapor pressure of the substance with the weakest intermolecular forces of the three is really high. That's because it doesn't take a lot to break those forces. But then again, the water has got a much lower vapor pressure in comparison because it has the strongest intermolecular forces. And then the boiling points are also dramatically different. Diethyl ether has the lowest boiling point, it has the weakest intermolecular forces. Water has the highest boiling point because it has the strongest intermolecular forces. Okay. Now, let's talk about substances that evaporate right away. If you have a liquid that has a really high vapor pressure, that means it evaporates very easily. This would be things like rubbing alcohol, acetone, which is a nail polish remover, and then gasoline. Now, these substances are said to be volatile substances because they evaporate readily. Do not confuse volatile with things that are explosive, okay? All right, let's take a look at the next page. Let's go to Dalton's law of partial pressures. So we started talking about gases being collected over water at the very beginning of this section. And anytime you read about a gas being collected over water, you're going to be using a version of Dalton's law of partial pressures, which says that the total pressure would be equal to the gas that's being collected over water plus the vapor pressure of water. So this right here is the vapor pressure of water, and you would obtain this value from the table that we earmarked on a previous page. And they will tell you the temperature that you're at so that you know what value to put here. Okay, so you might be collecting hydrogen gas or helium gas, and that would be the gas that you're collecting over water, and you're generally solving for this variable, okay? And then another version of Dalton's law of partial pressures is at the bottom of this page. So let's say you have a sample of a bunch of different gases, and you want to calculate the total pressure. You would add together the individual pressures of those gases. So if you take a look down here, Dalton's law of partial pressures is also, and I will give you this equation, the total pressure is equal to the individual gas pressure. So the pressure of gas A plus the pressure of gas B plus the pressure of gas C. They call these individual pressures partial pressures. So this would be the partial pressure of gas A or the partial pressure of gas B.